Hello, it's Keith here, and this is lesson 2 of my 8086 assembly programming tutorials. Now, we started last week looking at the absolute basics of the system. We just learned how to move a few values into registers and things like that. This week we're going to move on to the addressing memory modes. Now, the 8086, like most of these advanced processors, have a lot of different options with regards to addressing memory, and that's what gives the system a lot of its power. So what we're going to do this week is we're going to go through every single addressing mode one by one. We're going to see a practical example of that addressing mode and see how it actually works. And hopefully through that, some of the more complex ones will become a little bit clearer for you, because some of them are a little bit tricky and can be a bit confusing to understand what they do or how to get them working. So we'll go over the basics today and we'll have a look at each one. And once we've done that, we'll be able to progress to more complex things in the future, like branching and things like that. Okay, well, let's have a look at what we're going to be looking at first then. The first one we're going to be looking at is immediate addressing. You can see that just here. Now, that's not going to be something particularly scary because we've actually already looked at it. So let's go over to our code and let's see that in action. Okay, so this is the test lesson, lesson 2 here. So I'm just going to enable this first test here, and you can see it right here. And if we fire this up here, so here's our example running just here. So here's our source code and here's the results. So you can see we've got some monitor tools here that we're using to just show results to the screen here. And we're also dumping some bits of memory for some of the other tests. But we're going to go through the basics of each of these commands one by one, and we'll see the results that are occurring on the screen. So at the start of our commands running, our AX register was retaining the value 0013 here. And then we did a move command. And this is very much what we saw before, a value within the source code, 1234 in hexadecimal, being moved into AX here. And this is literally what an immediate value is. It's a value immediately in the source code. It's fixed, unless we're doing something crazy with self-modifying code, which is way outside of what we're going to be looking at here. But generally speaking, it's going to be fixed. It's going to be in your source code in the same line as the actual command itself. So you can see here we're loading a 16-bit value, 1234, into the 16-bit register pair, AX here. And you can see just from this monitor dump here that has occurred. AX now contains 1234 when this next execution of this monitor dump occurred here. Now, here we're loading a 16-bit value into a 16-bit register, but as we saw last time, we can load 8-bit registers as well, BH and BL. We can load with separate values here in hexadecimal. And if you missed last week's lesson, I certainly suggest you go back and look at it, but if you missed it, the H here stands for hexadecimal. Because the first character needs to be a digit, I've just put a 0 here for this 16-bit 255 here. So you can see we've loaded BX in two parts, the FF part and the EE part, into the high and low halves of BX here. And you can see the results just there. Now, that's how we load our basic registers A, B, C, and D. We do have the special registers, the segment registers, ES, DS, and so on. Now, these can't be loaded directly, so if we want to set these, we do need to actually set them in separate parts. And you can see we've done that just here. We loaded AX with this value and then moved that value into ES. Now, one thing I do have to point out at this point is that my monitor tools, the tutorial code, like these here, do use some of these segments, the data segments and things that uses those as part of the fonts and things. So just be aware that the monitor tools may not work correctly if you're changing the segments. So these examples will work, of course, but if you're playing around with them and you find things are breaking, it might be because you're changing the segments that those monitor tools are relying on. So just be a little bit careful there if you're wondering why your examples aren't working. Anyway, you can see here we're able to load a segment directly. We loaded ES with 1234 via AX here. And when we did our monitor here, you can see ES now does contain 1234 just here. Now, that's how we can load a literal value into a segment register, but that's not going to be the best way in most cases. We're going to want to load something that's actually relating to our program. So, for example, if we want to point the extra segment here to the code segment, which is what we're looking at right here, then we can use the @ symbol here, which tells the assembler to load in the address of the code segment into AX, and then we're transferring that into ES just here. And when we do our monitor here, you can see ES now contains 01A2. And we're actually dumping part of the memory here, and you can see 01A2 is indeed the code segment there. You can see just at the top half of this, there's a colon here, so that is working okay. Now, you might be thinking, well, I don't understand what a segment is. Don't worry about it. We're going to get to that in just a moment. I'm trying to do these things as simply as possible in stages, so I have to discuss the registers at this point, but we've not actually covered what they do. So we'll get to that in just a moment. Okay, so that was our immediate addressing mode. Let's move on to our next one, the register addressing mode just here. So let's go over to our code and let's see that. So register addressing mode again is nothing that we need to be particularly scared of. It's actually again something we've already seen. So let's fire up our source code here and just see it running. Okay, so this is the register addressing. And the register addressing just means that the data is being taken from a register. The values are registers. So in this case, we're just transferring the value from a register to a register, and that's what it means. So you can see here we're transferring a fixed value into a register, and here we're just transferring from and to registers here. So you can see, and if we look at our example code here, we've loaded AX with 1, 2, 3, 4 as a test value here, and then we've moved AH into BH, and you can see that the high part of BX has changed from 0, 0 to the 1, 2 that is in the high part of AX. And then you can see we've transferred the high part of BX, BH, into the low part, BL. And now you can see that both parts are 1, 2, 1, 2. And you can see we then transferred BX into AX, and it did the same. Now, of course, these are all very well and good, and we can transfer bits around registers, as you can see. We can also swap two registers without any kind of intermediary with the exchange command. This allows us to switch two over without any kind of temporary in between. But as I say, basically, register addressing is just where the value of the source or the destination is a register. So, you know, it's something that's really fundamental, and we have already seen it, but just wanted to go through it again for completeness. Okay, so that's our register addressing. Now, unfortunately, this is where things get a little bit more tricky, and we are going to have to discuss the dreaded subject of segments, which is really the point where the 8086 becomes rather difficult, especially compared to the 68000. Now, the 8086 was based on the 8080. It kind of has some 16-bit roots. So although it's a 20-bit addressing system, it can address 20 bits of memory rather than the 16-bit of the 8-bit systems. It's not a true 20-bit system in the sense that it doesn't have 32-bit registers like the 68000, that the addresses can work entirely within one register. And so the way that things work is when we want to use an address, we are basically specifying it in two parts. We've got the segment section, which effectively is the top 16 bits, and then you've got the offset segment section, which is either an immediate value or another register, and the two are added together. Now you'll notice those were both 16 bits and the total is 20, and you can see there's an overlap. So effectively the segment section is the top 16 bits, and then added to that is the address part here, and the result will be the sum of the two. And obviously these 4 bits would effectively be 0, and these 4 bits would effectively be 0. Now, I know that sounds a bit confusing. I mean, in all honesty, you just need to kind of think of the 8086 in the way we're programming it as being a 16-bit addressing processor, and you just need to make sure these segments are pointing to whatever data you need. So if the data is part of your code, you need to point it to the code segment. If it's part of the data section, which is a different part of your code definition in the assembly, you need to point it to that, and so on. And sometimes you might need to point it to the hardware, different areas of hardware for video memory and things. But as I say, in a lot of ways you kind of have to think of it as being a bit of a 16-bit system in that sense. Now we're going to go over this and we're going to have a bit of a look at these segments, and as I say, unfortunately they are a little bit frustrating, but we do have to do them. Now I do have to say at this point that in the later processors this was all sort of removed. They started using a linear model with the protected modes, as it's called, and things became a lot easier with the 386 and later. But as I say, in these early systems that we're covering in these tutorials, segments were definitely a thing. So that's what we're going to have to work with for these tutorials. Okay, well anyway, enough of that rather stressful talk. Let's go over to the code and let's hopefully see something that's a bit easier for us to understand. So we're going to be doing some memory addressing here. So let's just go to the example code here. Right, here it is. So you can see here we are just doing some work with the segments here. Now, whenever we specify an address that's to be read from, that's not a register or immediate, of course, we're loading from a segment, and the registers will all work from the data segment by default in general terms. So when we are specifying to load, for example, from the memory address 000C here, the code is going to assume that we mean the data segment 000C offset in the DS registers data segment. So you can see here I'm just initially setting the data segment to point to the code chunk here, and you can see I'm actually pushing and popping the data segment, which is backing up and restoring it. And the reason I'm doing that is what I said earlier, because my functions require that data segment to be what it expects them to be. So if we're going to mess with it, you've either not got to use my monitor functions, or you've got to make sure it's back to normal when you run them. So that's what we've done there. Now let's just have a look at our code segment right at the top here. You can see all the way up here is a section called some data, and this is just a little bit of test data. And you can see there's a jump here, so this won't start quite at 0, and that's why we've got that C in there. So we don't need to worry about that though, because we're actually going to dump the memory to the screen, so we'll be able to see what actually happened and what AX contains reading in from this value. Now, of course, you can see here there's some square brackets here, and that is telling the assembler to read in from the memory address of 000C, not the value 000C. That's what the square brackets do, and that's what we're doing here. So let's just fire this up. And here it is. So you can see here that this is the start of the test data, which is indeed 000C. This is the segment, as we saw before, that is effectively our code segment. Now, we can't be sure of that. It would depend on the operating system and things. It might be different. It's not always going to be 0, 1, A2, but in these examples with this emulator, it is. So you can see here, we've just monitored the starting values here, and then we've loaded in AX from 000C, which is, of course, these 2 bytes here. Now, you can see these are 0, 1, 2, and 3, but AX ended up with the value 2301. If this is your first time using assembly and you've not really come across this thing before, this is known as little endian. The vast majority of processors nowadays are little endian, and this means that the smallest part of the 16-bit pair will be stored first, and the highest part will be stored second. So effectively, this was treated as the low part and loaded in here, and this was treated as the high part and stored in here. And if we were working in 32 bits, you'd see that continue along the chain. So that's why we've got that 2301 value from a memory address that's stored 0123. It's perfectly normal and what we would expect. Okay, so that's loading in from a numeric immediate value, but that's not all we can do here. Now, what we can also do is we can load in from an address that we're specifying by a label. Now, you can see at the top here, some data is our label, which is, of course, that 000C that we've already discussed. And you can see what we're going to do next is we're actually going to load in some values from it. Now, first of all, we're just dumping the data to the screen once again here. You can see that just here. It's not changed, of course, but what we're going to do then is we're going to read in some values into registers from those addresses by using the label. Now, this time, rather than relying on it automatically defaulting to the data segment, we're going to specify to use the code segment CS. The code segment is the current running program, you see, and that's why we've got these default ones, and why the default is always to the data segment, not the code segment. But we can override it by specifying CS code segment, colon, and then a label, and we're specifying some data here. Now, the only thing is with 8086, the assemblers seem to get a little bit confused by this kind of thing. Other assemblers for 68000 and things wouldn't, but the 8086 ones, we actually need to specify that the data here is actually a pointer, and we want to load in from the memory address that's specified by that label. And so we are specifying the word pointer here, and I'm just adding an extra hint here to say, well, you're loading in a byte from this pointer, CS some data, and then here this is a word 16 bits. Now, if you don't put these bytes and words, it might come up with warnings, and I think it will actually often get it right. But for safety and to avoid as many warnings as possible, we probably want to specify it. So I'm specifying this is a byte pointer and this is a word pointer, and if you don't put this in, you'll get weird values. So that was something that caught me out in the early days. So if you want to load from an address label, just put in these byte pointer or word pointer before the address you're loading in. And again, we've got the address in square brackets here. So what have we actually done? Well, we're loading in our AL, which is the low part here, and we've loaded it in from the address some data, and of course that's just here. So we've loaded in 01 into here, and then in the next example we've loaded the 16-bit pair BX from some data plus 2. Well, here's the new value of BX, and you can see this is offset 0, 1, 2, so it's loaded 4, 5, 6 and 7, which again little endian, so it's become 6, 7, 4, 5 here. So that's why we've loaded in BX from offset +2 and why they've been swapped over. You can see it's because of the little endian and the offset from the label. So hopefully that makes some sense to you. Of course, what I'd suggest you do is download these source code examples, and if you're not quite clear, just have a play around and see what happens. Hopefully it'll help you out. So that's how we can read in from addresses using the byte pointer and word pointer and labels, or literal addresses numerically here. And this is probably going to be more relevant to loading in or writing to hardware, where the hardware has a fixed address. And this is probably going to be better for you when you're working with data within your code and data segments. Okay, so in this case, we're just reading in here, but really all of these addressing modes we can use as the source or as the destination. So we can do the same with the destination, and we're going to do that just here. We're going to use some OR commands, which we've not really covered yet, but we are going to get to them soon, don't worry about that. But effectively, we're just setting the top half of each of these, the top nibble as it's called, in AL and BH and BL here. We're just setting them all to Fs here, so you can see they've changed. And that's just so we've got a test value, and then we're going to write them straight back to where we came. So we're just writing the byte pointer destination here with AL, just like we read in here, and the word pointer here with BX here. And you can see here that 01 has changed to F1, and you can see here 4567 has become F5, F7, but 23 is unchanged because we only wrote a byte here, so the top half is unchanged. So that's how we can read and write to these addresses. Now, just one thing I'm going to show you here. So I've got a screenshot of the working code just here. And then what I'm going to do, just to make a point here, is I'm going to take these byte pointers out here. And if I run again, you can see that instead of reading in 01 here, it's now reading OC. And instead of reading 6745 here, it's now loaded 000E here. You can see that actually, I think it's loaded in the value of some data and some data +2, the labels, not the data in the address of those labels. So as I say, you do need to make sure that when you're intending to load from a label, from an address label in this way, you do need to specify byte pointer and word pointer, otherwise you're going to end up with a mess. And as I say, for me that was something that I really struggled with, but it is very important to get working code. So we've looked at how we can actually address memory there with some labels and with some direct memory values. Now of course we can do a similar thing with our registers. We can specify a register, and the value in that register will be the address that we read from. So let's have a go at that now. So if I just fire up this example here, again I say it's really intended that you should, if you've got time, if you download these examples, and hopefully you'll be able to test them all out yourself and make a few changes and see how those changes are affecting things. Okay, so let's see what we've got here. So once again, we're just showing the initial starting point, and this time we're going to actually read in the address of the sum data test values in a slightly different way. Now before we used @code to specify that we wanted to load the code segment address, but if we want to get the segment address of a specific label, we can use some assembler directives to do that. Here we're using the seg instruction, which will tell the assembler get the segment of some data and store it in AX, and we're transferring that to the extended segment here, ES, and that's done via AX again because we can't do it directly. So that's got the segment of some data's label, and then we want to get the offset within that, and we're doing that with the offset command here, and we're loading that into BX. And so now ES will be the segment of some data, and BX will be the offset of some data. We can use this pair to read in from the label of some data, because we've got that full 20-bit address that the 8086 needs to read in directly from a memory location within the addressable memory of the system. And that's what we're doing here. Now we're using the colon again. We did see that just up here, but before we were using a label. Well, this time we're using a register. So we're saying here, thanks to these square brackets, load in from the address in code segment ES offset BX here, and load that into AX. And that's what we've done just here. So as I said just before, BX now points to the offset of some data, and ES points to the segment of some data. So we're just reading in from these values just here. Now at this point you can see here that we've loaded in the segment here, 01A2, and you can see that just here, and that's been done by this command. And then we've loaded in the offset just here, and you can see that's just been done here. As you can see, that's the segment, that's the offset just here. And then what we're doing is we're loading into AX from that location. And of course, that location is this 0123 just here. And it's been loaded in, again, little endian just here. So we've been able to load in just fine here with this example. Now, of course, we can do this with other registers other than the A, B, C, and D. So in this case, we're going to use the DI register here, and we're going to load in from offset some data plus 2. And again, we're just having to specify the ES segment here, because otherwise it would default to DS in this kind of form. And then, thanks to these square brackets, we're loading in from the address in ESDI here, and loading into BX just here. And you can see just here, we've loaded in 4567, which has become 6745 because of the little endian, and that's this pair just here. Offset 0, 1, 2 from the start of our test data, the sum data label. So there we go. So we've loaded in just there. Now, if we don't specify ES colon, it would have defaulted to DS. Now, in this case, that's not what we're going to want. So, as I say, you've just got to make sure that if you don't want to load in from DS, you need to specify the alternate segment. I do have to say that if you don't specify the segments, you actually save a little bit of memory, because the extra specification, I believe, increases the size of the instructions in memory. But as I say, for these examples, we're not going to be worried about memory really, so that's not a concern for us, but it could be if you've got a very big program. Okay, so that's register indirect addressing, where we use a register as the address. But there's going to be even more advanced stuff we can do. We might want to have a numerical offset from the value in the register. And now let's take a look at that. Okay, so here's the example we're going to be doing, this indexed, which is known as based or indexed addressing. Let's fire it up just now then. Now this is effectively where we are specifying an address by using a register as the base position and then specifying a fixed numerical offset like an immediate that is going to be added to that address. You might be thinking, why would you want to do this? Well, let's imagine you have a two-player game with 2 human players, and each player's got a bank of data that remembers the current position of the player, the score of the player, things like that. Well, when you want to do the same rules and controls for player 2, you wouldn't want to have 2 pieces of code with different addresses specifying the different pointers to the player's memory. So what you would want to do is you would want to set one of your registers to point to the start of that player's memory, and then use offsets for the XY position, the score, the player sprite. And then when it comes to player 2, you just change that address to the second player's information, and the offsets would stay the same. Now, of course, that's just one very simple example, but there'll be lots of other cases you'd want to do this. Addressing some kinds of hardware, you would set the address pointer to the start of that hardware, or indeed software if you're using a system call, and then you would use the offsets to change the parameters or indeed do calls. So this is something you see quite a lot in programming, and of course the 8086 supports this for us. Now when we want to do it, all we do is really simple. Just like before, we're specifying our address here with the BX here, and we're just putting +1 on the end here, and that is the offset from BX, and that will read in just fine. So what we're going to do here is we're going to load in the offset to some data in BX, and you can see that's happened just here. And then we load in AX from the address in BX encode segment +1 here, and then we have loaded that into AX, and you can see that has happened just here. So you've got 4523, which is the BX address is pointing here, then +1. So we've loaded in 2345, and thanks to little endian, that's become 4523. So you can see that has indeed happened just there. Then what we've done is we've added 2 to BX, and we are just now changing the values and saving them back here. And you can see that that has happened. They've been written to just here. So the point I'm making here is we can change our offset here in BX. We can use these offsets here as a fixed value, and all of this will work for it just fine. As I say, it's really handy for when you're trying to use a set of past parameters or something in a block, and you want to set the address to the start of that block in your register, and then use those fixed offsets in this way. So that's going to be really quite useful to you. Now, in this case, we've just used a numeric value in line, but we might want to use something known as symbols. Now, if we've got our defined block of player variables, for example, and the first one is the sprite address, and then then 3 bytes in, that's the X position, and the 4th byte is the Y position. Well, we don't want to have to remember all those numbers, and they may change at some point. So rather than just putting numbers in line in this way, what we actually probably want to do is define them as what's known as a symbol. So let's say we've got a symbol called second variable, and we're going to define that as equaling 2. Now we can then use, once we've defined that name second variable in our code, and the assembler will just convert it for us. So in this case we've just done bx plus second variable, which is exactly the same as writing bx plus 2. The benefit of this is if later on that becomes plus 6, we just change it in this one place and all of these other references stay the same. And you can see that we've done that just here. So in this case we've got bx again pointing to the start of our data here, and we've loaded in ax from the second variable here, and you can see that that has loaded in F3, F5 here, and that's become F5, F3, a little endian there. So that's been loaded in from plus 2 here. But then when it comes to the third one, we've actually loaded in 6655 here into the third variable, which is an offset of 4, 0, 1, 2, 3, 4, and you can see 6655 has been loaded in there, again in little endian. So again, we can use these symbols, and this is going to be in most terms the easiest way for you to work with them, because you won't need to remember these offsets, and if they change you can change them in just one place. But you can see here we can use these both as a reading source and as a destination for writing, and they'll work just fine. Okay, so now we're on to base plus indexed addressing. Now this is kind of similar to what we saw before, but this will actually use the sum of two registers. So rather than just having one register and using that as the source address, we can actually use the addition of a second register, and we will actually still get a result. And this is going to be quite a powerful one, because it does allow us a lot more flexibility, and it does allow us to use non-fixed offsets in a similar way as we saw before. So let's go over to the code and see this one in action. Let's fire the example up then. Okay, and let's have a look at what we're doing here then. So you can see here that we're just loading in some sample values here as before, and we're just loading di as equaling 1 here, and we're just showing the value of all of these registers to the screen. So you can see the base pointer BP is pointing to the start of our test data here. We've got a test data we're pretty familiar with now, I think. And so when we load in from AX in the extended segment, which is just pointing to this segment of some data, plus the base pointer, which is pointing to some data, plus the DI register, which is just pointing to 1, then we're loading in, you can see here, 4523, because the offset of 1 is loading in 2, 3, 4, 5, little endian, it gets swapped around. Now we can then increase our base pointer, and we can move a value into BX, and you can see that has happened here, 4, 5, 6, 7, because we're now loading in from not 1 but 2 offset here, 4, 5, 6, 7. And as well as increasing our DI pointer, we can increase our base pointer. We've increased it by 2 here, so we've loaded in just here, because the offset, the starting point is now here and the offset is still 3, so we've loaded in CDAB into BX just here. And you can see this gives us some more flexibility. We can have a pointer that's the start of the array in the case of BP, and then we can use an offset that we can increment through if we're reading in a stream of data here, and you can see that just here. Now there are some clever commands known as string commands for reading in sequentially, but we're going to look at those later. So as I say, these are just very simple examples here, but that's what we can do with base plus indexed addressing here. Very powerful. Now that's pretty impressive, but the 8086 even goes further. So we can actually do things with what's known as base plus index with displacement addressing. So this is something that's way beyond what I was used to in the limited systems I've done. So let's have a look at this one. So let's go over to the code and have a look. So here's the example here. Now it's a new addressing mode, but it's really covering what we've already seen. Basically, this is a combination of the last two. We've now got a base register, an offset register, and an immediate fixed value here. And all of these are going to be added together and used as the source of the data here. So if you can see here, we've got our example here, and we are loading in all of our registers here. So DI equals 3, and our base pointer points to the start of our test again. And then we're loading in DI as 3 here. So now DI equals 3, and our base pointer is pointing to here. So that's offset to 1, 2, 3. But then we're adding an additional 1 immediately just here. And so we're loading in 89AB here, and that's becoming AB89 because it's little endian. And then we're loading in BX with an extra offset plus 2. And so you can see BX is equal to ABCD because it's reading in this pair here. You can see this is really quite a powerful option here, And once again, we can use symbols. Now, if you're looking at other people's source code, there is alternative ways that this can be specified. I prefer to specify the +1 here within these square brackets, but you can also put the +1 outside of the square brackets. That is exactly the same functionality, it's just a different way of representing it. And if you're using symbols or numbers, you can actually put them before the square brackets like this. So these all have the same meaning as the example we saw here. But as I say, for my preference, I put them in the square brackets. I think it makes it clearer that what's happening with regards to the calculation. So that's my preferred way. But if you're using other source code, you may see alternates. So just bear in mind they are the functionally same thing and don't worry about it. Now, I've specified plus values here, but they don't have to be positive. They can also be negative. So we can have a minus value here. And so we can do positive or negative values as an offset if we need to. So that's all quite handy. Now, all of these have effectively loaded in from the addresses into the register. But if we just want to calculate the address once and then store that in another register without actually reading from that address, we can do that with load effective address. Now, when we're doing these long calculations of multiple different parts that are all being summed together, that's going to potentially be a little bit slower than directly using an address. So what we can do is we can do that calculation once, and then if we need to do lots of inks later on of that resulting address, we can do that. So we can load in the effective address of this calculation, remember not the data at that address, the actual calculated address itself, into AX, and then we could do lots of inks of AX if we want here. And if we just have a look at our sample code here, you can see that we've loaded in the effective address AX just here, and you can see that has been calculated as being the base here, C, plus DI, which was +3, so DEF, but then -2, which brings it back to D, so that's why we've got that here. But then when we do a -3 here, you can see that BX becomes 0C here. So we can actually calculate the offset here and store the result with LEA into those registers. Now, there may be cases where we need to load a full 20-bit address into our segment register and our regular register simultaneously. And we have special commands called LDS and LES to do that. Now, these will use a pointer. If I just find the pointer here. Here it is. So you can see here we've got a word pointer pointing to a label here. And these will actually load in both the segment and also the address simultaneously. And we've got two special commands for that, LDS and LES here. And DS will load the data segment and also the specified register BX here. And LES will load the ES, the extended segment here, and also the AX register here. And in this case, we're loading both with the offset to some data pointer here. And the sum data pointer here is pointing to the label sum data, and it's the address of that sum data that we're loading in to those registers. You can see that both have been loaded just here, and if we look at DS and ES, they have indeed both been loaded with the address 01A2 just here. So that's how we do it. That's how we can load in an address in a true 20-bit sense on this system using both the segment register and the regular registers at the same time. Okay, well that was quite a long lesson. We've gone over an awful lot of content there. I know that might have been a bit confusing for you. I kind of apologise, but I wanted to make one lesson that covered it all. Now, we're going to go over lots more programming examples, and to be honest, some of these modes you probably won't need. You know, the very complex ones with multiple additions, you can certainly avoid using them if they're not needed by your code. But as we're doing an 8086 tutorial, I wanted to cover all the options available and also give you an introduction of how they work so that you at least knew that they were there, even if you decided not to use them. Anyway, I hope you found this interesting. If you caught this episode as your first, please go back and look at episode 1. We're going to be continuing forward with episode 3, and there's plenty more episodes coming where we're going to be looking at things like the stack, how to do branches and what have you. But I needed to go over this content today and just give you a proper breakdown of all the addressing modes. And these addressing modes can be used as sources and destinations in many of the other commands we're going to be seeing. So anyway, I hope you found this interesting. If you have, you know, please like and subscribe, you know, because there's lots more coming. If this was a bit tricky for you, I'd suggest you have maybe a look at Z80 or 68000 if you want to do some programming on a classic system. But this is just a bit tough. Then those are kind of more easy systems that you might find more luck with. But anyway, whatever you decide to do, hope you'll enjoy programming. I hope you enjoy the 8086. Thanks for watching today, and goodbye.